Well, hello, welcome again to Math 315, and this is the second video for Chapter 3 on series and summability. So we saw in the previous recording about what we mean by the definition of an infinite sum, which is the limit of the partial sums, and we looked at geometric series and telescoping series, and I finished off by just making a rather silly analogy perhaps between our infinite series and dividing up a pizza. But that is actually a useful analogy, and we'll use it again shortly when we look at the harmonic series. So continuing on, here's another example here. We've got sigma k on k plus 1, where k is 1 to infinity, and I claim that this one diverges. And we can see that because we start to work out the nth partial sum. So we put k as 1 in, so I get 1 over 2, and put k as 2, I get 2 over 3, 3 over 4, and so on, and the nth one will be n on n plus 1. Now if you look at these numbers here, each one of these is actually bigger than the first one. So 2/3 is bigger than a half, and 3/4 is bigger than a half. And in general, n on n plus 1 is bigger than a half as soon as we get past the first term. So I can say that this partial sum is bigger than, well, I copy the first term, and then this is bigger than a half, this is bigger than a half, they're all bigger than a half, and there are n of these. So if I add up a half n times, I just get a half of n. And the point is that that goes to infinity as n goes to infinity. In other words, in this example, the partial sums are not finite, and that means this infinite series diverges. Now, what's making it diverge? Well, what's making it diverge is if we look at the general term here, if we just take a limit of this expression here, k on k plus 1, as k becomes very big, then this is not going to 0. This is the limit of this one is going to 1. So the terms are not getting smaller. They're not going to 0 as we take more and more terms. So it's sort of fairly evident that if the terms of the series are not becoming small the further out we go, then the series has not got much hope of converging. The terms have to be getting smaller. Now that's a very, very important result, sometimes called the nth term test or something. So I'm going to write it as a theorem. And here it is. It says if the infinite series sigma an converges, then the limit as n goes to infinity of an is 0. That is, the general term has to go to 0. If the series converges, then the general term goes to 0. Now note that the converse of this is false. In other words, just because the general term goes to 0 does not mean that the series necessarily converges. It's what we call a necessary but not sufficient condition. So when you're looking at an infinite series, say something like this one here, the first thing I look at is look at the general term. If that's not going to 0, then I'm finished. The series must diverge. It cannot converge unless the general term here is going to 0. And that's a fundamental fact. But be careful, as I said, the converse is false, as we'll see. Now I've done just a little, it's actually quite easy to prove this result, so I've done a little quick proof of this one here. So if we suppose that this infinite series converges, and by the way, I'm not saying where it begins here, sometimes I will, sometimes I won't. It doesn't matter whether this starts at n equals 1 or whether it starts at n equals 1,000. It doesn't change whether the series converges or not. Then that means the limit of Sn exists. I suppose I should really say the limit as n goes to infinity of Sn exists and equals S, say. Now, if we take the difference between Sn plus 1 and Sn, we take the sum of the first n plus 1 terms minus the sum of the first n terms, well, I just get the nth term. And if I now take a limit in this equation here, then the limit of the partial sums are both going to s. So the limit of this as n goes to infinity is s, and the limit of this as n goes to infinity is also s, and that of course is the limit then of a sub n as n goes to infinity, and s minus s is 0, and that means the limit of the general term is 0. So there's a little proof of that fact. So if we apply this now to the theorem to this series here, and I'll do that over here. This is very easy now. Here's our sum, and the general term of this sum now is n on n plus 1, and that goes to 1 as n goes to infinity. That tells me the general term is not going to 0, and that means the series diverges. So one of the first things we check with these infinite series, we look at the general term and see what is this doing. If it's not going to 0, then the series diverges without doing anything more. Now I'm just going to summarize here just a couple of basic properties of series. Firstly, we're going to suppose we've got two infinite series of real numbers, and that they converge to capital A and capital B respectively. That means this one converges to capital A and this series converges to capital B. And I take any two real numbers alpha and beta. Then if I look at the series alpha times AN plus beta times BN, then if these converge, then this converges as well, and as you'd expect, it's just going to converge to alpha A plus beta B. The second point here says that adding or subtracting a finite number of terms to a series does not affect convergence or divergence. So if we add a finite number of terms or subtract to a series, that does not affect the convergence or divergence. Now that's one of the reasons why sometimes I won't bother writing where n begins. So because of this fact, we often just write this without making specific reference to the starting value of the summation index. We'll just write it like that. You can sum when n equals 1 to infinity, or you can sum n as 1,000 to infinity. It's not going to make any difference to whether the series converges or diverges. It will make a difference, of course, if it converges to the value of the sum, but not to whether it converges or diverges. Now, I want to introduce now a very important series called the harmonic series. And it looks like this. It's 1 plus a half plus a third plus a quarter and so on. And that's sigma 1 over k, k is 1 to infinity. Now, for historical reasons, it's called the harmonic series. It's because of the fact this is related to what was called the harmonic average or the harmonic mean of a set of numbers, an idea which goes in fact back to the ancient Greeks, but the name comes from there. It's just for historical reasons, but we're going to call it the harmonic series. Now I want to go back to my rather silly analogy of the pizzas again. And so using that same pizza analogy I mentioned above, so what happens? You call a party, you go on Facebook, you invite everybody, and an unlimited number of people turn up. Not a wise move, as I said. So suppose the first person to arrive at the party gets one whole pizza. There it is. Lucky them, they get one whole pizza for themselves. And so what do? Well, you better order another one. The next person that turns up gets half a pizza. And the next person that turns up gets a third of a pizza. Now the trouble is then, in order to give the next person the equivalent of a quarter of a pizza, well, you need to order another one, because if you take a half plus a third plus a quarter, you get 13 twelfths, and that's bigger than 1. So by the time the fourth person turns up, you have to order another pizza. Well, you keep going, the next person gets a fifth, the next person gets a sixth, the next person gets a seventh, and it turns out, I think, that by the time you get to the 10th person, whoops, you've run out of pizza again and you've got to order another one. So you continue in this way, and the question is, how many pizzas do you have to order so that everybody, the nth person, gets 1 over nth of a pizza? And we're going to see that this is not a good move, because we're about to see that you need to order infinitely many pizzas. And sorry, again, there's some slight typos here. So we're about to see, it turns out you will need to order infinitely many pizzas in order to satisfy each person, or give each person something. Now, so in other words, what I'm going to show is, I'm going to show that this infinite series here diverges. That this sum keeps getting bigger and bigger and bigger, and it diverges to infinity. Notice the general term does go to 0, 1 over k goes to 0, but the infinite series nonetheless does not converge. Now, the way we're going to do this, there are various ways of doing this. I'm going to look at the partial sums s sub 2n. S sub 2 to the power n, I should say here. So I'm going to take the number of terms n to be a power of 2, for convenience. So here we are. Here's the partial sums of the first 2 to the n terms. So I get 1 plus a half plus a third plus a quarter plus a fifth plus a sixth and so on. And finally, the last one is going to be 1 over, k is going to be 2 to the n. So I take 1 over 2 to the n. And you'll notice that I've bracketed these together in a certain way. I've bracketed a third, I've taken 1 plus a half, I'm going to bracket a third and a quarter together. Then I'm going to, so I've got 2 terms here. Now I'm going to bracket 4 terms together, a fifth plus a sixth plus a seventh plus an eighth, that's 4 terms. In the next bracket, which I haven't shown, I have 1 over 9 plus 1 over 10, all the way up to 1 over 16, so I've got 8 terms in that bracket. And I keep going, and the last bracket I do this with. So that's the last bracket there. Now, just have a look at what's happening in each bracket. In each of the brackets, every term is larger than the last one. That is, a third is bigger than a quarter. In this bracket, a fifth is bigger than an eighth, a sixth is bigger than an eighth, a seventh is bigger than an eighth, and so on through all these brackets. So I can say then that my partial sums going up to 2 to the n terms is bigger than, well, I copy 1 plus a half, and now I say a third is bigger than a quarter. Then I'm going to say a fifth is bigger than an eighth, the sixth is bigger than an eighth, the seventh is bigger than an eighth, and an eighth equals an eighth. And finally, in the last bracket, this term is bigger than this one, and same all the way through. Now, when we come to simplify this, and here's the punchline here, a half plus a quarter is a half. And an eighth plus an eighth plus an eighth plus an eighth is a half. And in every one of these brackets, they all add up to a half. So I'm going to get 2 to the n minus 1 terms here, times that's going to give me a half. So I get a half plus a half plus a half n times, and I can add that up, that's just n times a half. And that was the partial sums up to 2 to the n is bigger than this thing. So my conclusion then is the partial sums taking the first 2 to the n terms is bigger than 1 plus n over 2, and that goes off to infinity. And that tells me then that I need to keep ordering more and more pizzas in this scenario, because the partial sums are getting bigger and bigger and bigger. In other words, the harmonic series diverges. Now, you don't need to be able to reproduce that proof, but it's just a nice example of how we can use inequalities to show this particular harmonic series diverges. The important fact is that this series diverges. That's what you should know. So note then that although the general term 1 over n is going to 0 as n goes to infinity, the series does not converge. Sigma 1 over n does not converge. Now it's very important here, as I mentioned before, to clearly distinguish between the series and the terms of the series which form a sequence. So when I look at sigma 1 over n, this is a series which diverges, but the individual terms, an is 1 over n, converges to a half. So make sure we distinguish between the series and the terms of the series. Well, we've just seen that the sigma 1 over k, this harmonic series, diverges. Well, what about sigma 1 over k squared? What if I take the sums of the squares? Now, what does this look like? Well, this looks like 1 on 1 squared plus 1 on 2 squared plus 1 on 3 squared plus forever. So we now take the reciprocals of the squares and we add them all up. Can we make sense of this one? Does this sum converge? Well, this was, people knew this converged, but nobody knew quite what it converged to until Euler came along. That famous mathematician Leonhard Euler worked on this sum, in fact, when he was a relatively young university student, and he showed that it converged. And he even found the real number it converged to. And you may know this, that it converges to pi squared on 6. And that is a remarkable fact, that if you take 1 on 1 squared plus 1 on 2 squared plus 1 on 3 squared plus 1 on 4 squared and you keep going, that infinite series converges, and it converges to pi squared on 6. And it is remarkable that pi suddenly turns up here, because after all it's got nothing to do with pi here, and yet the sum turns out to be pi squared on 6. This is a beautiful result. And we may, at some later point, be able to give some kind of proof of that, but we'll see if we have time somewhere. Now, I'm going to give you a geometric proof, not the fact that it's pi squared on 6, but a geometric proof using integration that this thing converges. Now, this is a nice example. Again, you should have a look at this one. There'll be a couple of problems similar to this in the tutorial problems we'll have a look at later on, but see if you can follow through the reasoning here. So what I'm going to do is I'm going to consider the area under the curve f of x is 1 on x squared from 1 up to some positive integer n. So here's the picture. There's the function f of x is 1 on x squared. And I'm going to just write some numbers down here. I'm going to put 1, 2, 3, 4, up to n minus 1, and then n down here on the x-axis. So these are integers. And I'm going to draw some rectangles. So I'm going to draw a rectangle there, rectangle there, rectangle there, and so on. And I've got dot, dot, dots in here, so there's lots of other little rectangles in here. And I'm going to work out the area of each of these rectangles. So for each of these, the width of each of these rectangles is 1. Wherever you go, the width is always 1. Now, what's the height of the rectangle? Well, this rectangle I've drawn like this, so the height's going to happen at 2. So I put 2 into the function, so I get 1 on 2 squared. So it's going to have a height of 1 on 2 squared, width of 1, so the area of this rectangle is 1 over 2 squared. Similarly for this one, the width of this rectangle is 1. I put 3 in there, I get 1 over 3 squared. So the area of this rectangle is 1 over 3 squared, and so on. The area of this rectangle is 1 on 4 squared, and at the end I get 1 on n squared. Now you'll notice that these rectangles approximate the area under the curve, because there's little gaps here. So if I add up this area plus this area plus this area up to here, then that's going to be less than the area under the curve from 1 up to n. It's going to be less than the area under the curve from 1 up to n. Okay, so now comparing areas and triangles, of rectangles, then my partial sums of this series here, so that's 1 plus 1 on 2 squared up to plus 1 on n squared, and that's going to be 1 plus this thing is less than the area under the curve, 1 on x squared, from 1 up to n. Now you can do this little integral over the side. I'll just do this here. We're going to work out the integral of 1 on x squared from 1 to n dx. So this is the integral from x to the minus 2 dx. So we increase the power by 1, divide by the new power from 1 up to n. So that's minus 1 on x from 1 up to n, and that's going to be minus 1 on n plus 1. So we just do a little bit of integration over the side there. You should try and do that one yourself. Just check that integral is correct there. And then I've got 1 plus this one, so that's 2 minus 1 on n, and the point is that's less than 2. That's less than 2. So that means the partial sums then are all less than 2, and because I'm adding on something each time, the partial sums are bounded above by 2. The partial sums are getting bigger because every time I move to the next partial sum up, I'm adding in something. And so now I can use that lovely monotone convergence theorem, and tells us that the partial sums are converging to something. We're not sure what it is at this point, but to some real number which is less than 2. And in fact, as I said, the exact value is pi squared on 6. Now, I might pause there at this stage, give you some time to have a think about that last example and to copy the material in, and we'll continue this in the next recording.